Okay, thank you for the introduction. As said, my name is Anna, and I'm here to talk to you today about scheduling context capabilities. So, looking up here, my claim is that the operating systems of today are insufficient for the cyber-physical systems of tomorrow. So we're talking about self-driving cars, autonomous planes, smart factories, you name it. So, in this talk, I will define what a mixed criticality system is, why you should care about it, what a mixed criticality system needs from the operating system, our model for doing that, and then some very, very tiny highlights of the implementation and evaluation in the SEL4 high assurance microkernel. So, first up, the criticality of a system refers to how bad a failure can possibly be. So a high criticality system like airbags, object avoidance, landing gear in a plane, it's highly critical because failure can cause massive death and destruction. Whereas a low criticality system, something like music playing in a car, a failure can only really cause a degradation in service. We don't mind that much. Now, traditionally, software of different criticalities was separately run on different hardware. So they couldn't possibly interfere with each other. This doesn't really work anymore. Because safety critical systems have a lot of over-provisioning, it has resulted in way too many processors in cars and airplanes. It's a problem for size, weight, and power constraints. And it also prevents us from building the systems we actually want to build. So consider a self-driving car. You might have systems that use infrared to detect pedestrians and to not hit those. You might have cameras for other object avoidance. You might have information coming from a traffic service. These all need to talk to the car and tell the car where to drive, but some are more important than others. An air gap isn't going to work here. So enter mixed criticality systems, where we run software of different criticalities on shared hardware. So the problem is, without strong spatial and temporal isolation, everything in the system is promoted to the highest criticality level. And high criticality software is very expensive to develop. The higher the criticality, the higher the assurance levels required. And higher assurance not only means it's very expensive to develop, but the software itself is generally much simpler, so we can get worst case execution time estimates and generally test the software as best we can. So you're not doing things like heuristics in a really high criticality piece of software. So the challenge for operating systems for mixed criticality is, how do we provide that isolation? Now there are two types, spatial isolation and temporal isolation. We know how to do spatial isolation, which I will cover very soon, but this talk is mainly about temporal isolation. Now let me introduce you to some background from the real-time community. The sporadic task model is a popular way to model tasks to make sure that they meet all of their deadlines, which means that they are correct. If they don't meet their deadlines, people are going to die. So it's modeled, tasks like a thread is modeled as an infinite series of jobs. They wake up at a certain time, like an interrupt comes in. They execute for a defined worst case execution time, and they reoccur every period. They arrive at the purple up arrows, and when the red down arrows come, if they haven't executed by that time, we're in a bad place. So you might be thinking, I learned about this in uni, it's fixed priority rate monotonic, it's solved. So let me explain why that is actually insufficient. So under fixed priority rate monotonic, you order all of your tasks by their rate. The fastest tasks with the shortest periods get to run first. And as long as the total utilization of those tasks is below about 70%, it's schedulable and everything is fine. Finished. Not really, because you're trusting those tasks to behave, and predictability implies trust. Also, the priorities that you have assigned have nothing to do with how critical those tasks are. So if we look at this example I have of 3 tasks, A, B, and C, they're schedulable. The sum of the utilizations is less than the magic number we need. But they'll only meet their deadlines if we order them by the rate monotonic priority, which, in my very convenient example, is the opposite of the criticality. So we have this high priority task. If it doesn't behave and overruns its time, it could cause failures in the really important task, which we don't want. That violates temporal isolation. Okay, So I said that in SEL4 we know how to do spatial isolation. We do this by having capabilities, an access token. We pass a capability to all of the memory in the system at the start, and the initial task can then break up that memory however it wants. It can slice it up, hand it out, delegate to subsystems, and this allows us to have spatial isolation without applying any restrictions on user level policy. And this is what we really want for a small trusted computing base. What about temporal isolation? It would be very nice if we could do the same thing for time and say, here's 100% CPU, let's split it up and hand it out. Unfortunately, by me being here, you've probably guessed that you can't do that. So, why? The basic reason is because time isn't fungible. You can't replace one piece of time with another piece of time and expect everything to be fine. So here we have two tasks meeting their deadlines, all of them are executing, like A and B are both executing, their execution time gets there before the red down arrow, everybody's happy about that. If we swap two pieces of time, everybody isn't happy, we missed a deadline and something very serious happened and now everybody is dead. So, we can't treat time the same way. Now, ARINC 653 is a current standard for mixed criticality avionics software. And it means that you have to statically partition everything. So you can only schedule partitions, there's no changes, there's no dynamic things there. And the reason this doesn't work very well, I mean, it works, but it's not very efficient because each partition has to be made for the entire worst case execution time of a task. So when you're looking at a really high criticality task, which has a worst case execution time, probably orders of magnitude beyond the actual observed execution time, you have to reserve that entire partition. And then your best effort task that's low criticality can only use the little fragment of CPU that's left over. So while this works, we want more flexibility than that. So that brings you to the actual model. We introduced this new kernel object called the scheduling context. You can have capabilities to them. And they represent an upper bound on execution. We separate them from the traditional thread. We still have the thread which contains, the execution context, the register set, stack, all of those things. But the scheduling context is separate. This gets configured by user level, but enforced by the kernel, and it doesn't contain a priority, the reason for which will become clear very soon. Okay, the parameters in the scheduling context are a worst case execution time and a period, and there can be two different types of them. You can either set the worst case execution time to be equal to the period, in which case it's just a round robin thread, and it'll behave exactly as previous threads did. It's fully backwards compatible with the kernel. But you can also have a partial scheduling context where the worst case execution time is less than the period, and this is an upper bound the kernel will enforce. It's not a lower bound, and it's not a guarantee that you'll get the time. It's just a guarantee that you can't exceed the time. And if you don't have a scheduling context, threads can't be scheduled. And there's just one thread, one scheduling context. So there's no two-level scheduling here. We modify the existing scheduler. So the current, traditional L4 scheduler is just 256 priorities. Within a priority, things are scheduled via round robin. We just have a linked list for each priority. So we add, as well as the invariant that you can't be in the scheduler without a scheduling context, we add a new queue of threads, that is threads waiting for more budget. They don't have any bandwidth available. The kernels put them in the release queue to wait. So that's very simple. Now, we also add a new capability called the scheduling control capability, because when you create a scheduling context, it's a memory object, but it's all zero. It's not worth anything. So anybody with memory can create a scheduling context, but good luck, you can't do anything with that. So you need this scheduling control capability to configure a scheduling context for a specific core. So the initial task gets one scheduling control capability for each core, and then it can run admission tests or configure the scheduling policy at user level, at startup, or dynamically. So here is our model. You have admission control at user level. This could be static. You could have done everything offline and you just have a static admission control that sets everything up and goes away, or it could be running a more dynamic service. You have your mixed criticality threads running on the kernel, and these have been assigned scheduling contexts. Now, the kernel will enforce those parameters in the scheduling context and pick the highest priority thread that's runnable. Very simple. You'll also notice that there is a lock on the screen, This represents a shared resource, which we want to share between tasks of different criticalities without promoting them all to the highest level, which I will now cover. Okay, resource sharing in SEL4 is modeled as RPC. So we have a server which acts as a critical section, and tasks send inter-process communication messages to that server in order to get the server to do something for them. An example in a mixed criticality system is something like the server represents the waypoints that an aircraft might need to go to, and you have all of these different inputs coming to the server, like communications from the ground, which is less critical than, say, the flight control, which is stopping the plane from destabilizing or crashing into a mountain. But these need to share this service. And the server itself runs at the ceiling priority. Scheduling contexts don't contain priorities, so we don't enforce that the server runs at the ceiling priority, but if you want to avoid priority inversion, then it's a good idea to do that. So how does this work with scheduling contexts? Well, we preserve the default behavior, where you can have your server has a scheduling context, all your client threads have them, and when you make a request, the server charges its own scheduling context for any execution time. This, of course, doesn't give you any temporal isolation. If I only get 20% of the CPU and the server gets 100%, then I can execute as many requests as I want and effectively denial of service other clients. So we introduced a new concept called passive servers, where the server itself does not have a scheduling context. When you make an RPC call, the scheduling context travels to the server, and the server charges that scheduling context, which gives you the temporal isolation you need. When the server replies, the scheduling context goes back. Now the client can't make any more calls than the bandwidth that the scheduling context represents, which is neat. You might be wondering, what happens when the client's time runs out in the server? Because we trust the server, but the server doesn't trust its clients. We have another mechanism for this, which is called a timeout fault, which is raised. Each server can have an optional timeout fault handler. The timeout fault is sent to that, and it can do whatever it wants. This is a user level thing. The timeout fault handler just gets a notification saying, hey, this has happened, and then it can do whatever is appropriate for that service. So that might be something like rolling back the server to the last known state, some kind of bandwidth inheritance, really whatever is appropriate for that system. It might be more things like if it's actually representing a device, doing some kind of emergency reset, whatever's appropriate. So I've implemented all of this in SEL4. I'm currently working with our proof engineers to get this through verification. We already have a specification for it. There's an exploration of the implementation in the paper, and a full evaluation, but I'm showing one benchmark with you here. So here we have two clients, A and B, and they're sharing a trusted AES encryption service. So we set the budgets of each one to be the opposite of the other one. So if A has 2 milliseconds out of every 10, B has 8. And when the timeout exceptions come in, because they're asking for a large amount of data to be encrypted, and they have various insufficient budgets to do so. So constantly temporal faults are coming in, and the server rolls back to the last clean state. And because the algorithm processes in blocks, we just lose the last block we were working on. And you can see that the throughput scales with the budget. So we have temporal isolation, which is a good thing. Okay, to summarize, we provide temporal isolation through scheduling contexts, which are configured by user level, but enforced by the kernel. Scheduling context donation over IPC is used for shared server isolation, and timeout exceptions for timeout exceptions. There's way more in the paper about how we do with multi-core, what the enforcement algorithm is, an implementation of user-level EDF, which is compatible with this. All the code is on GitHub. All the benchmarks are on GitHub, so you can have a look at it there. And thank you. Questions?
Excellent work. Quick question, when you have a timeout, whose budget is used to process the rollback or the timeout?
Timeout exception handlers need their own scheduling context. Otherwise, you just shot yourself in the foot because the timeout exception handler can't run. So you need to set that. And it's of course going to be trusted, so you could set that to have its own 100% CPU allocation. Of course, you need full analysis for that.
Thank you.
So I have sort of a practical question. If you're going to do this in a safety critical system, then you have to convince some kind of certification body that you're doing something good.
Mhm.
So do you see some aspects of your approach that would help you make such a case for your approach?
Yeah, I mean, we're currently working to convince certification authorities that SEL4 is better than what they currently have. But that's a process we're going through with industry at the moment.
Okay.
That answers
So
the
does
question.
your approach contribute to it in some way, or?
It follows the story in that
Okay.
it provides more isolation than we had previously, and it will be verified for correctness as well.
Okay. Further questions? Okay, thank you.
So the next speaker is Ming Huang, who's a associate professor at Arizona State University.
Hi, my name is Ming. So I'm an associate professor at Arizona State University. Jorge Cabrera is my PhD student. He's currently on leave. That's the main reason why I'm presenting this work instead of him. So our work is about supporting time-sensitive applications in virtualized computing systems, such as public and private cloud systems. We know that cloud computing has already achieved greater success. Many applications can already be enabled in the cloud. The main reason behind the success of cloud is cost effectiveness, right, and scalability. But how about time-sensitive applications? We don't see a lot of success with enabling time-sensitive applications in the cloud. And then when I say time-sensitive, we are mainly considering two types of applications. One type is applications with soft deadlines, and the other type is applications that don't really have deadlines, but they require low latency. They have maybe a tail latency target. So we see that, we believe that the main challenge to supporting these types of applications in the cloud is because the success of cloud is based on resource consolidation, high resource consolidation. And because of the high level or high degree of consolidation, there's complex and dynamic contention among the virtual machines. And time-sensitive workloads are unfortunately particularly vulnerable to this contention. And what makes this problem more difficult for the resource management system is that there's a lack of awareness between the virtual machine host and the virtual machine guests. And to be more specific, the host does not know what kind of applications are running in the guests and what are their requirements, and also the guests do not know the host, the resource allocation, resource management decisions made by the host. Here I use a very simple, almost toy example to illustrate why this lack of awareness creates a problem to support time-sensitive applications. So in this simple example, I just quickly go through it. So we have 3 virtual machines sharing a single CPU, and this Gantt chart shows that we have enough CPU bandwidth to satisfy the bandwidth requirements of all the 3 virtual machines. But if when we look at the 2 time-sensitive applications running on VM1, the way that the dialines of how this applications are aligned to when the virtual machine is given time to run, we actually make the second application miss every other dialine when it is scheduled. Again, the reason is because even though there's enough bandwidth to satisfy everybody's requirement, but because the host schedule cannot give the virtual machine, the application running on the virtual machine, the bandwidth when they really need the bandwidth. As a result, they cannot always meet their deadlines. So to solve this problem, our solution is called RTVert. Our solution is based on 2 levels of work. First, we designed a new virtualization architecture which allows the guest and the host to communicate and cooperate on scheduling. And this cooperation has to be low overhead because we're trying to support fine-grained timeliness requirement. And based on this framework, then we also created new cross-layer schedulers that are able to work together and deliver strong timeliness guarantees. For example, we're able to meet 99% of all the deadlines or support a 99% latency target. And when we achieve both these strong timeliness guarantees, we are also able to make efficient resource utilization. Okay, compared to a state-of-the-art related work, we save up to 50% of the CPU bandwidth. So, of course, our solution is not complete. As a first step towards a more complete solution, we have made many assumptions. Our focus is on CPU scheduling. So we support CPU-bound applications, but we do want to support applications with different levels of timeliness requirement, and we also want to support dynamic applications and virtual machines, which means that the application of virtual machines, they can come and go at any time, and also their requirements can change at any time. We believe these are very important to applications in the cloud. So I already introduced the problem background. In the rest of my talk, I will explain the architecture algorithms, scheduling architecture algorithm of RTVert, experimental evaluation, and finally the conclusions. So in terms of architecture, so we made the decision to keep the existing 2 levels for schedulers in the virtual machine system. In the existing system, we have the process schedulers in the guest and the virtual machine scheduler at the host in the hypervisor. We decided to keep these 2 levels of schedulers because we believe that is important for better scalability by separating the concerns of process scheduling from virtual machine scheduling, okay, using the 2 levels of schedulers. But in order to support time-sensitive applications, we want these 2 levels to cooperate. Right? That's what we mean by cross-layer scheduling. We want to enable cross-layer communication and cooperation on scheduling. And more specifically, the guest schedulers can inform the host on application timeliness requirements in terms of the bandwidth requirements and deadlines, etc. And the host schedule can also notify the guest virtual machines that the resource allocation decisions. Now, based on this architecture, okay, so then let's look at the interfaces that we are exposed to different layers in this architecture. Okay, on this architecture. So instead of the guest, at the application level, we actually use existing system call interfaces. Okay. For example, on Linux, there's a system call called a set attribute. Okay. That is a system call that an application can use to register itself and its real-time requirements with the operating system process scheduler. So we reuse that scheduler so that we do not make any change, we do not require any change on the applications. We believe that's very important. So we can support, our solution can support unmodified applications. But at the host level, we use to allow the guest and the host to cooperate on scheduling, right? Then for that, we use a pair virtualization interface. So more specifically, we added a new hypercall that's called RTVert, and also a new piece of shared memory between the guest and host for sharing critical information. Okay. So by doing that, of course, we are trading complete transparency for improved timeliness. Okay. So our principle is the same as the reason for pair virtualization. We are trading transparency for some some other aspects of the system, right? In this case, we are trading transparency for improved timeliness. Now, let's look at the schedulers at the guest level and the host level. The guest level scheduler is actually pretty simple. So we in fact use a simple partitioned ETF scheduler. The only thing I want to emphasize is that instead of using a global ETF scheduler, which is supposed to be optimal than partitioned scheduler, we assign the application to different vCPUs, and our guest level scheduler schedules the processes that are assigned to a particular vCPU. So the processes are not allowed to migrate, and that is good for us because it makes it really easy for us to determine the bandwidth requirement of each vCPU because processes don't migrate. It also helps us avoid the overhead from process migration. But by doing this, we do not sacrifice resource efficiency because the vCPUs are allowed to migrate, okay, and map to different PCPUs. So as a result, we can still achieve nearly full system utilization. So that's the trade-off that's the decision we made, and it worked out well for us. At the host level, schedule is a lot more complicated than the guest level. So we want our schedule to be optimal. We want to be able to do optimal multiprocessor scheduling. So what that means is that if the total amount of available bandwidth is greater or equal to than the total amount of required bandwidth from all the applications, then we must be able to schedule all the applications. Okay, that's what it means. So in order to accomplish that, we based our scheduler, our host level scheduler, on a existing optimal multiprocessor scheduler. It's called DPRAP. So DPRAP was created for non-virtualized system. So, we adopted and extended to make it work for virtual machine scheduling and to support cross-layer scheduling. So I don't have time to go into details of DPRAP, but the basic idea of a DPRAP is that it will consider consider all the tasks deadlines as deadlines for everybody, and those are called global deadlines. And the time slice between two consecutive global deadlines is called global slice, and global slice is partitioned among the tasks according to their bandwidth requirements. Okay, that's just basic idea. Now, to make it work for RTVert, so what we did in this cross-layer version of DPRAP is that the host schedule will use DPRAP to schedule all the vCPUs according to the vCPU's deadlines, okay, and according to vCPU global deadlines. Okay. And then so instead of us using DPRAP schedule processes, we use DPRAP to schedule vCPUs. So the next global deadline is the earliest deadline of all the vCPUs. And then the global slice is the time slice between two consecutive global deadlines from the vCPUs. Okay? And then we partition the global time slice among the vCPUs in the same way how DPRAP works. And then the vCPU's bandwidth requirement is shared with from the guest to the host by using the new SkyVert hypercall, and the global deadlines are shared from the guest to the host by using the shared memory. So in summary, this is our design. So we have two level schedulers, and they work together. The applications use the existing system call, and no change required. And the guest communicate with the host using hypercall and shared memory. So now let me present our evaluation results. So we did our prototype based on Zen and Linux, and we consider a variety of benchmarks. I will explain them shortly when I present the results. But in summary, we have considered both synthetic applications, which allow us to vary the parameters conveniently, and real-time applications, including both a video streaming server that has soft deadlines, and also a in-memory data store, memcached, and that has a tail latency target. And we compare to Artisan, that is the state-of-the-art real-time virtual machine scheduler. It is based on the SASA theory, which is a traditional real-time hierarchical scheduling theory. And we also compare it to the default Zen schedule, which is credited. So I want to spend a little bit of time on the first experiment, although it's based on synthetic benchmark, but it allows us to explore the space, the design space quite conveniently. So here in this graph we show, so first of all, so we in the table we show the parameters of all the applications that we considered, and the bottom bar graph shows the CPU utilization achieved from RTVert versus RTZen. And so first of all, both RTVert and RTZen are able to meet all the deadlines. Okay, so in each group bars, the right bar, with the green shaded bar is from RTVert, and the gray shaded bar on the left is from RTZen. So the several observations we can make from this result. First, RTVert is highly resource efficient because compared to the right shaded bar, which is the total bandwidth, the raw bandwidth requirement from all the applications, RTVert requires just a little bit more than what the applications really is. Okay, so our overhead in terms of resource utilization is really low. And then compared to the gray bars, which is the amount of bandwidth that needs to be set aside for real-time applications in the Artisan solution, we can save up to almost 40% of a CPU bandwidth. All right, so let me very quickly go through the next two experiments. The second experiment is we want to study how we can support dynamic applications. So we use video streaming servers. Just forget about this chart, that's too complicated to explain, but in general, we run a total of 54 streaming servers, and they came at different times, and also left at different times, and their bandwidth requirements were also set dynamically. Okay? And this kind of scenarios cannot be supported by Artisan or other existing works, but we can support it really well. Out of all the 54 streaming servers, only 5 of them had data misses, and at most 0.1% misses. And this is the last experiment I want to explain. This is also important because here this is an application that does not have deadlines but have a tail density target. And so we compare to 2 different Artisan configurations. Only one of the 2 is able to meet that tail density target. And we also compare to Credit. And Credit is interesting because Credit actually delivers the best average latency, but it misses the tail latency target miserably. Okay? So overall, this experiment shows that RTVert is able to meet the tail latency target and save 50% CPU bandwidth compared to the Artisan configuration that actually works. All right, so I skip scalability. So now, there are a number of related works, so we're absolutely not the first one studying this problem. I already mentioned Artisan is quite pessimistic and does not support dynamic applications. There are also works that took the cross-layer scheduling approach, and which were published before. And in those 2 works, they consider only simple host-level scheduler, and which is not optimal, and they also cannot support dynamic applications. Finally, to conclude, so we feel that supporting strong quality of service in general is still an open problem in cloud computing research. And in this work, we focus on the strong timeliness guarantees for the software real-time applications and the latency sensitive applications with the efficient resource utilization. And in summary, RTVert is by doing cross-layer scheduling is able to meet 99% of deadlines, or meet a 99.9% latency target, and it can support diverse CPU-bound applications in a dynamic environment. And there are, of course, many future research opportunities. First, we want to consider other important resources such as I/O, and also we can consider end-to-end timeliness guarantees across multiple hosts. All right, so I want to acknowledge the sponsors, my team, and thank you so much for your attention, and our code is also open source.
What's your resource management model? Or put differently, if I have a VM on your cloud, can I just monopolize the processor by saying always I have very tight deadlines?
Yeah, that's a very good question, yes. So first of all, we do have a limit on how small your deadline can be. Okay? So that limit in our implementation is 250 microseconds. Okay? So you cannot go lower than that. That will help us solve that problem partially. And also we think that for in the cloud computing environment, right, it doesn't help the users to claim more than what they really need, right? Because you have to pay for what you claim, not what you actually need, right?
Okay, but can you charge for timeliness? Do you have a model for doing that?
I'm sorry?
Do you have a model for charging for timeliness? I mean, if I...
Yeah, right. So that will be the next level question. If this is adopted in the real cloud environment, then we can do that, yes.
What's the motivation for using a global optimal scheduler? Because those are known to incur quite some overheads and not scale so well. And in addition to that, have you looked at peak throughput under RT-Vert and the baselines?
Peak throughput. So just because the fact that we can support more, so that's just the experiment I skipped. That's a scalability experiment. So we can see the 100 real-time applications, and we are able to support more than Artisan. Right? So that tells us that we can achieve higher. So we have support up to 100, and I think the detail in the paper, Artisan can support up to 90. Right? So we achieve at least 10% more throughput than Artisan. Okay? And so scalability, I think, is also a relative term. So for us, we are able to support up 100 real-time applications, maybe a couple of hundred applications should be okay. So that tells us, using a optimal multiprocessor scheduler is okay for our, at least in this context. Yeah, of course, if I go for even larger numbers, thousands of applications, we haven't tried that yet, and I'm sure there will be challenges. Yeah. Thank you.
Okay, so the next speaker will be Manohar Vanha from the Max Planck Institute for Software Systems. He's a PhD student.
Okay. Can everyone hear me? Okay, so yeah, I'm Manohar Vanga. I'm a PhD student at MPISWS in Germany, and this is joint work with my colleague Arpan Gujarati and my advisor Bjorn Brandenburg. All right, so the work in our paper is motivated by how to support high-density VM workloads. And what I mean by high density is simply where you have many VMs, many small VMs packed onto a few number of cores. Well, why should you care about high density? Today, the cloud market is fairly competitive with many big players, and this is driving improvements in data center efficiency in an effort to better utilize resources. And one approach that helps is high-density VM packing, where you can consolidate resources by taking these small, cheap VMs and packing them onto a few number of cores. Now, of course, the challenge is how can you achieve this while keeping your customers happy? Because you still have to continue to provide consistent throughput, consistently high throughput, and predictable latencies, in particular tail latencies. And this is where one of the key pieces of the puzzle is essential to overcoming the challenges of high density, and that's the VM scheduler. The VM scheduler in a hypervisor is analogous to a process scheduler in an OS, except it deals with virtual CPUs instead of processes. And in a high-density setting where you have many VMs per core, you end up having many allocation decisions made at runtime, CPU allocation decisions. And suddenly your VM scheduler performance can have a serious impact on application throughput and latency. So let me show you an example from the Zen hypervisor that demonstrates exactly how VM scheduling can affect application performance. We ran a very simple experiment on a 16-core Intel Xeon server running 4 VMs per core. And we measured the HTTPS performance of one of these VMs running Nginx, while all the others were doing some kind of IO-intensive background workload. And I'm going to present the results in this kind of graph here, where on the x-axis you have the observed throughput in requests per second, and on the y-axis you have the 99th percentile latency that we measure. And of course, lower is better on the y-axis, more to the right is better on the x-axis, because we want high throughput and low latency. And I'm going to present results for two Zen schedulers, Credit and RTDS. Credit is the default fair share scheduler that's within Zen. This is typically what's used in production today. RTDS, on the other hand, is a somewhat recent addition. It's a real-time scheduler aimed at latency-sensitive workloads, and it derives from the RTZen project. And this is the curve. These are the two curves we get when requesting random 100 kilobyte sized files from Nginx while this IO background workload is running. So let's look at the results for Credit here. Well, first we see that Credit provides much higher throughput, almost 600 requests per second. However, you also see that Credit has increasing latency tails as you get to these higher throughputs. Already at 550 requests per second, we're seeing over 100 milliseconds of 99th percentile latency. RTDS, on the other hand, actually has quite consistent tail latency characteristics across its throughput range. So until it reaches its peak and suddenly spikes up, it does pretty well on tail latency. Now, of course, the throughput itself is severely limited, almost 30% lower than Credit. So in this paper, we propose a new VM scheduler design called Tableau. And Tableau actually is aimed at simultaneously achieving both high throughput and predictable tail latencies. And we actually achieved this, and I'm going to talk about that. Tableau is a somewhat unorthodox design. It's based on static table-driven scheduling, and it's tailored specifically for high-density public clouds. In the paper, we showed that Tableau is efficient in that it incurs low overheads, runtime overheads. It's predictable in that it enables very accurate control over the scheduler-induced delay, which I term scheduling latency, and it's high throughput. In particular, it provides very high SLA-aware throughput, which is the maximum throughput given a certain bound on tail latency. All right, so the rest of the talk, I'm just going to briefly talk about the design, present some results, and conclude. All right, so what do we really want from a VM scheduler? It's really just two things. We want it to be as invisible as possible. That is, you want it to have low runtime overheads, and you want to provide certain guarantees for every VM in the system. In particular, you want to guarantee a certain utilization, which is a share of the CPU time, and you want to ensure there's some predictable bound on the scheduler-induced delay, scheduling latency. Now, if you think about it, requirement 2 is a fairly non-trivial problem to ensure a certain utilization and predictable bound on latency for every VM in the system. And attempting to do this at runtime kind of conflicts with requirement 1, right? You cannot have complex decision-making and low overheads. So how do we actually overcome these conflicting requirements? Well, Tableau exploits one very key property of VM environments, which is that the VM churn on a single server in a data center is low. And when I say low, I mean relative to the process creation rates and scheduler activation rates, which is on the order of milliseconds. You have VMs being created and destroyed on the order of minutes, if not hours or longer. Right, so we have these two requirements. To satisfy requirement 1, we chose a table-driven dispatcher, a very simple design. All it does is schedule an arbitrary table that's provided to it, and this table consists of VM allocations over time, and it blindly follows this table. And this table is of a finite length and just repeats forever. And we feed this dispatcher with a table that's generated by a semi-offline planner. And what I mean by semi-offline is simply that it's running asynchronously in the supervisory VM. And we make this planner fast by applying techniques from hard real-time systems. And the interesting thing is we only need to invoke this planner whenever we create a VM. There's no other point in time where we have to actually invoke this. And this approach has a very nice feature, which is it clearly separates mechanism and policy. The dispatcher is completely unaware of VM-specific requirements. All it sees is a simple table, and all it does is blindly follow this table. And the advantage of having this policy done asynchronously in the supervisory VM is you can easily extend this using very high-level languages, tools, and libraries. You can also do all kinds of tricks to get rid of the time it takes to generate tables, such as pre-generating tables for certain common scenarios. You can cache tables, or you can even generate these on a separate machine. For example, you could generate these at the cluster level scheduler itself. So while assigning a VM to a server, in addition to assigning it, you also start building the tables. Okay, so how do we actually generate these tables that satisfy all these constraints? I want to briefly talk about this. So in Tableau, every VM is configured with two parameters: a utilization that determines how much CPU time you get, and a bound on the scheduling latency that it's willing to tolerate. And I want to point out that this is no more information than existing schedulers require. So for example, credit requires a relative weight, which determines the utilization, and it requires a global time slice that ends up determining the scheduling latency you will see. And so this is somewhat equivalent. The first step we do is model these as periodic tasks, which is one of the classic task models from real-time systems. And once we have these periodic tasks for each VM, we just partition them onto individual cores, and then we apply some recent scheduling techniques from real-time systems to get our table. And I won't talk about the technique itself in detail. You can see, you can look at our paper for that. So again, this is performed entirely in user space of the supervisory VM, and ours was actually implemented in Python using a fairly mature library called SCEDCAT, which provides a lot of the real-time primitives that we make use of. All right, I briefly want to talk about that one transformation where we go from this utilization and maximum scheduling latency to this periodic task. Because once we make this transformation for each VM, we can then apply a whole bunch of literature that's been done, that's been published in the real-time community on dealing with scheduling periodic tasks. Okay, so what we want is to go from a VM that's defined by utilization and scheduling latency to a budget and a period. And this is what a periodic task looks like. You have a period P and you're guaranteed a budget C within that period. Now, if you think about it, the worst case scheduling latency occurs when you get all your budget at the beginning of one period, but only at the end of the next period. And this is just 2 times P minus C. And once we know this, we can actually bound this using L and pick values for P and C that satisfy that constraint. All right, so again, as I said, I won't go into details on the table generation itself. You can find them in our paper. But how long does it actually take to do this whole thing? How long does it take to actually generate these tables? On this graph on the x-axis, you see the number of VMs on a 48-core server. And on the y-axis, you see the time it took to generate tables. And I'm going to show results for 4 different scenarios where all the VMs were configured with a scheduling latency of anywhere between 1 and 100 milliseconds. And of course, lower is better because we want shorter table generation times. And this is what we see. So what we see is the time it takes to generate tables is always under 2 seconds, even for the somewhat extreme scenario of all VMs being set to 1 millisecond on a 48-core machine with almost 180 virtual machines. In the more normal case, so the 1 millisecond is somewhat extreme because it results in sub-millisecond slot sizes, which is not very practical. So in the more common case, this is on the order of a few hundred milliseconds. All right, so table generation times are fairly reasonable, especially when you compare it with the time it takes to create or shut down a VM. In addition, what's important to note is that this is done asynchronously. So VMs begin running immediately. As soon as they're created, they start scavenging any idle cycles in the system and begin booting up. What takes time to kick in are the guarantees that these tables provide. Right? And as I mentioned, you can hide that latency in many ways. You can cache tables, you can pre-generate them, you can generate them externally. All right, so I want to briefly talk about the mechanism itself. We had an implementation of Tableau in Zen, which is a popular open source hypervisor, and it creates this supervisory VM when you boot Zen up. Within Zen, the hypervisor itself, we implemented a simple table-driven dispatcher. And in user space, we had a daemon that's responsible for regenerating tables whenever VMs are created. And this was about 1,600 lines of Python. Now, this is a non-work conserving scheduler, where if the table dictates that the core should idle, even if there are runnable VMs on that core, the core will idle. And this is actually not so unreasonable in a cloud setting where you don't want to give more resources to a customer than they're paying for. However, there are cases where you want work conserving behavior, in particular with regards to mean latency. And so what we do is have a second level scheduler that takes over whenever the first one idles, and it picks runnable core local VMs to schedule. And that's it. That's the whole design of Tableau, and it's an intentionally simple design. So does it actually work? So in the paper, we show that Tableau incurs lower runtime overheads than the other schedulers we evaluated. This is not surprising. It's just a table lookup at runtime. It also enables much more accurate control over scheduling latency. Again, not surprising. It's based on hard real-time scheduling theory. And I'm going to talk about the third one, which is that Tableau achieves higher SLA-aware application throughput. Again, SLA-aware application throughput being the maximum throughput you can achieve given a bound on tail latency. So you can see the paper for details on the first two. I will talk about the third. Right, so our experiments were run on these 16-core Intel Xeon machines running recent versions of Ubuntu and Zen. And we had two of these machines connected by 10 gig Ethernet, one for generating the load, the other one hosting all the VMs. And we tried to simulate a multi-tenant data center environment. That is the kind of environment that Tableau is aimed at. We had 4 VMs per core, and we measure the performance of one of these VMs while all the others are performing some kind of background work using the stress-ng tool. And for the most part, schedulers were configured with their default configurations, except when there were well-known best practices. So in the case of credit, we use a 5 millisecond time slice instead of the default 30 millisecond one, which is known to perform poorly for I/O workloads. And then we come up with an equivalent configuration for the other 2 schedulers. Okay, so again, I'm going to show this graph where on the x-axis we have the observed throughput, y-axis the 99th percentile latency. And again, lower is better, more to the right is better. Okay, so here we care about 2 metrics, peak throughput and SLA-aware throughput. I'm going to talk about peak throughput first. So peak throughput is the maximum throughput you can achieve regardless of the latency that you're willing to tolerate. And here we see that Tableau actually achieves the highest peak throughput. Credit is actually quite comparable in peak throughput, but its latencies begin to rise much sooner. And RTDS, of course, has significantly lower throughput. On the other hand, if we draw a horizontal line across, in this case at 50 milliseconds, what we get is what we term SLA-aware throughput. So what's the maximum throughput you can achieve given a bound on scheduling latency? And here we see again that Tableau achieves a much higher SLA-aware throughput than the other schedulers. Credit already at a 50 millisecond SLA is comparable in performance to RTDS. Now, one of the limitations of using a table-driven approach is that you incur higher mean latencies. In particular, when you have hard-capped VMs that are only allowed to execute within their slots, you end up seeing slightly higher mean latencies. Now, this is not surprising because if you have a slot for a VM and your request shows up just after you finished your slot, you have to wait till the next slot to execute. And so this shows up as higher means. And we can see this here in this graph, which is exactly the same as before, except for 1 kilobyte files. And I've replaced the 99th percentile on the y-axis with the mean latency. So we see that due to this rigid table-based scheduling, Tableau incurs a slightly higher mean overhead. But you actually have a lot more control over this because this depends on the scheduling latency that you pick for the VMs. In that sense, Tableau provides more control. And the other thing to note is that Tableau is much more predictable. That line is fairly straight until you actually hit that peak throughput. So to summarize, Tableau incurs lower runtime overheads and enables more accurate control over scheduling latency, not too surprising. And as I showed, it results in higher SLA-aware application throughput. And although hard caps VM under Tableau incur a much higher or slightly higher mean latency, this is controllable through the scheduling latency parameter. And To conclude, I presented Tableau, which is a somewhat unorthodox approach to VM scheduling based on table-driven schedulers. We showed that Tableau is efficient, predictable, and high throughput. In particular, it provides high SLA-aware peak throughput. Thank you. And all source code is, of course, available.
Okay, thank you. Very nice talk. So I have two questions. So with the cap in place, is your scheduler still work conserving? And the second question is, how does your scheduler handle the fluctuations of the VM workload? So it's safe to assume that when the VM is active, then you have a predictable workload or demand. But what if the VMs, especially for the highly consolidated environments, you could have a situation that the VMs could have interleaved of idle periods and the busy periods. So what if a VM is idle? Then do you need to recalculate your table for the scheduling for the set of VM? Thank you.
Okay. So with regards to your first question, there's a difference between capping and non-work conserving versus conserving. You can have hard-capped VMs in conjunction with uncapped VMs, and then you have a work-conserving scheduler, because the uncapped VMs will take over any idle slots in the system. With regards to your second question, we see this more as a scheduler used by the cloud providers to essentially create fixed type of VMs, which you then give out to customers. So you would upfront know what the performance of a VM is when you purchase it. And if you really wanted to do this in an internal data center style environment, you would basically build tables that provide the guarantees that you need for peak performance so that you can handle the workload variation that occurs. Thanks.
Okay, so the next speaker will be Jung-Sub An from Aju University in Korea. He's an associate professor there.
Okay. Thank you for the introduction. Hello, everybody. I'm Jung-Sub An from Aju University. Today, I'm going to tell you about how we are able to minimize the negative artifact of CPU consolidation by introducing flexible micro-sliced code. This is a joint work with my colleagues at KAIST, Changhyun Park, Taekyung Ho, and Jaehyuk Ho. Let's start with the server utilization issue. We already know that server utilization is critical for efficiency in clouds as well as data centers. This graph shows a typical case where traditional computer servers are underutilized on average. So what we'd like to do is move this hump to the right to have higher utilization for the large fraction of time. So consolidating multiple virtual machines into fewer servers can significantly increase resource utilization. However, sometimes unexpected performance degradation occurs because of resource contention. So in this study, we focus on CPU sharing problems among virtual machines. Let me go through what things can happen by sharing CPUs. Basically, to virtualize the limited number of physical CPUs, time sharing technique has been essential. So you notice that virtual CPUs are not always executing on physical CPUs. Each virtual CPU is periodically scheduled in and out by the underlying hypervisor. We call this virtual time discontinuity. Although time sharing can provide the concurrent execution of virtual machines, their executions are not physically continuous. What I wanted to point out here is that virtual CPUs are serving not only application thread, but also guest operating systems. The thing is, traditional operating systems have been designed under the assumption that operating systems can seed the physical CPUs at any time. But in fact, this assumption cannot be guaranteed in virtualized environment. Although Linux has adapted various patches for virtualized environments, it is still in its infancy. So when you run with Linux virtual machines, you may experience performance degradation. Let me introduce where the degradation comes from. First, in commodity operating systems, spin lock synchronization is widely used to protect short critical sections. We measure the average waiting time to acquire spin locks using kernel while running the GMAC benchmark building Linux kernel in parallel for two cases, solo and current. We observed that the lock processing time is largely amplified in 4 kernel components when running with a core-runner VM because lock holders are frequently preempted. Second, the processing time of interprocessor interrupts on which TRB synchronization relies is significantly delayed in terms of average and maximum latency. If a virtual CPU receiving an interrupt request is not executing on a physical CPU, the interrupt cannot be handled until the next scheduling turn of the virtual CPU. So here, DDoP and BIPs from parsec are known to excessively incur the TRB synchronization through the mmap and unmap system calls. In addition to that, the processing time of IO interrupt can be significantly delayed in mixed current environments, which means a virtual machine serves both CPU-intensive and IO-intensive together. In such a case, both jitters and throughput of IPERF benchmark are highly affected. Let me briefly review the basic concept of time-sharing systems to get a sense the root cause of the degradation. This figure exemplifies a case where 3 virtual CPUs share a physical CPU in a given time. Unless we limit the number of virtual CPUs to the number of physical CPUs we have, there is no way to entirely eliminate the waiting time. So it turns out that virtual CPU 0 needs to wait to be scheduled again until other virtual CPU 1 and 2 consume their time slice. In this state, to minimize the waiting time, the straightforward technique we can think is to shorten the time slice. Since spin locks and interrupts we've seen before actually require a short period of time, around 100 microseconds, to be completed in solo run, so shortened time slice might be effective. However, sometimes it becomes problematic because it causes frequent context switches, so which result in the pollution of architectural resources such as caches, TRBs, branch predictors, and so forth. So our main strategy is to achieve the advantages of short time slice while minimizing the negative effect which comes from the frequent context switches. So we divide the CPUs in a system into 2 groups. One is called normal pool on the left-hand side, which has the default time slice, and the other one is called the micro slice pool on the right-hand side, which is configured with short time slice. By maintaining the 2 different CPU pools, we are able to reconcile the 2 different requirements from applications and critical OS services. Application thread will be running on the normal pool as usual so that they are not going to experience the downside of short time slice. On the other hand, the critical OS services we've seen before, which are supposed to be rapidly completed, will be served on the micro-sliced pool so that we are able to minimize the waiting time. Here are 3 things we need to address to enable our approach, accelerating critical OS services with the micro-sliced pool. First, we need to be able to identify and detect the critical OS services because we do not want non-critical OS services as well as the applications to run on the micro-sliced pool. Second, we'd like to avoid the guest OS modification because requiring guest OS modification is not desirable in cloud systems. Last, statically partitioning CPUs into 2 groups may waste CPU utilization if applications are not kernel intensive, so that the micro-sliced pool becomes idle. So we develop a technique dynamically adjusting the number of micro-sliced cores. Let's first look at how we are able to detect the critical OS services. Basically, we analyze where virtual CPUs are frequently preempted by inspecting the instruction pointer. Specifically, whenever a virtual CPU is about to hit its physical CPU, we read the instruction pointer of the virtual CPU to get a sense what the virtual CPU is doing in kernel. Here, the reason why we focus on the yield exception is that in consolidated environment, the number of yield exception is soaring. So basically, yield is supposed to occur when there is no work to do, or somehow it cannot make forward progress. So we need to pay attention to the yield events. However, the instruction pointer itself does not have much information. It is just a memory address indicating an instruction. So to obtain the semantic of the address, we take advantage of the kernel symbol table. It gives us a hint to understand what the virtual CPU is doing in the kernel execution without OS modification. Here, let's say the instruction pointer is matched with a kernel function marked in red, then we are able to know where the virtual CPU is executing part of kernel. So the thing that I wanted to emphasize here is that the hypervisor is able to extract the meaningful information of guest operating systems from the instruction pointer with the symbol table. Through the methodology I've described before, we analyze the virtual CPU scheduling logs, which include the information of context switches for each virtual CPU, so that we figure out where the virtual CPUs are frequently preempted during the kernel executions. So based on this profiling information, we summarized the critical guest OS components on the right-hand side, which are frequently preempted in the consolidated environments for the Linux operating system. You can also take a look at the detailed table in our paper. So leveraging instruction pointer and kernel symbol tables make it possible to precisely identify and detect the critical OS services without guest OS modification. Let me give you a learning example from detection to acceleration. Here, let's say the virtual CPU 3 is spinning a log for a while, but it cannot acquire the log because the log is already held by another virtual CPU in this example. So the yield exception occurs on the virtual CPU 3. At that time, our hypervisor starts inspecting the instruction pointer to figure out the reason of the yield. Here, we need to inspect the preempted virtual CPU siblings as well to find who is likely holding the log. Let's say the virtual CPU 0 is suspected because it was running in a critical section according to our inspection. Then, we wake up the virtual CPU 0 on the micro-sliced pool so that it can rapidly release the log so the virtual CPU 3 can acquire the log within a short time. This is how our basic schemes work. Since the log can be held by only a core, so a single micro-sliced core would be sufficient. However, let's see the case where a single micro-sliced core is not sufficient. A representative case here we introduce is the IPI interprocessor interrupt-based TRB synchronization, which requires all the CPUs in the system to participate in the process of the operation. Let's say virtual CPU 0, 1, and 2 are preempted while virtual CPU 3 is in the middle of TRB synchronization. In this case, virtual CPU 3 cannot complete the operation because other siblings cannot send the IPI acknowledge to the IPI initiator virtual CPU 3. So the yield exception occurs on the virtual CPU 3. Here we may want to accelerate all the preempted virtual CPUs on the micro-sliced pool. In such a case, a single micro-sliced core would not be sufficient. So we have the ability to dynamically adjust the number of micro-sliced cores based on the event profiling. The events such as interprocess interrupts, pause loop exit, and IRQs are already monitored in the hypervisor, so it does not require huge engineering efforts. If we decide that a single microslice core is not sufficient from the profiling, then we dynamically increase the number of microslice core like this animation. Also, we are able to shrink the microslice pool if needed. Let me slightly move on how we are able to detect critical I/O events. I/O events occur externally, so the mechanism detecting critical I/O events differs from the earlier one glancing the instruction pointer. Here, once a physical interrupt occurs, let's say a packet arrives, then the interrupt is usually intercepted by the hypervisor, and the hypervisor generates a virtual interrupt to the target virtual machines. Finally, the guest OS will generate the virtual IPI to let the application know the data packet is prepared to be consumed. In the case of virtual machines having multiple virtual CPUs, the I/O handling becomes complex. In this example, we may want to accelerate both virtual CPU 0 and 2. But although commodity hypervisors are already designed to accelerate the IRQ and IPI, they have not considered the correlation between two signals occurred in an I/O event. In our study, once we figure out the correlation, we accelerate the virtual CPUs on the microslice pool together so that those virtual CPUs do not wait for a while. To evaluate the effectiveness of our scheme, we built a virtualized systems by using Gen Hypervisor and deployed the two virtual machines. In our server, there are 12 physical hardware threads, and we configured the 12 virtual CPUs for each virtual machine. So the total 24 virtual CPUs share 12 physical hardware threads. We ran dedup and bips from Parsec and also evaluated a couple of benchmarks from Mossbench. In this talk, I will show you the result of XSIM, which is a main server and GMake parallel build. You can also find the result for other benchmarks in our paper. For the CPU pool configuration, we fixed the time slice of the microslice pool to 0.1 millisecond, and the normal CPU pool follows the default configuration of the Gen Hypervisor. Let me show you the performance result of our two schemes, static, ideal, and dynamic. On the x-axis, there are two virtual machines for each scenario, and y-axis show the execution time, so that the lower bar means the better performance. Here, our core runner serves swaption, which is a benchmark in Parsec. We picked the static ideal configuration from experimental results by betting the number of microslice cores manually. The number above the bar indicates the number of microslice cores used in the static ideal configuration. Our static scheme shows improved performance compared to the baseline. In addition to that, our dynamic scheme shows comparable performance in general compared to the static one. It slightly increased the execution time compared to the static one, but it is not significant at all. This graph shows the throughput improvement of XSIM benchmark on the y-axis, and x-axis shows our static and dynamic configurations. In this graph, we've seen our schemes show better performance than baseline while minimizing the slowdown of core runners. Especially the dynamic scheme outperformed the static one. To understand the benefit, we measured how many yield exceptions can be reduced by our schemes. In dynamic configuration, we've seen that the yield is further decreased by 8%. Our scheme also improved the I/O performance in mixed core run environment where virtual machine 1 serves both I/O-intensive and CPU-intensive applications together. In microsliced, the network bandwidth is significantly improved, and the jitters becomes more stable in microsliced core setting. Let me quickly conclude my talk. In this work, we introduced a new approach to mitigate the virtual time discontinuity problem. By leveraging the instruction pointer and kernel symbol table, we are able to precisely detect the critical OS services and avoid the guest OS modification. We also employed a dynamic technique to adjust the number of microslice cores so that we can adapt the load changes in the system. Lastly, we didn't see much overhead for applications which do not frequently use operating system services such as spec CPU. Thank you for your attention. I will take questions.
Hi, Boris Grant, University of Edinburgh. Really interesting work. I wonder, so to what sort of, I mean, it sounds like this is completely automated, but I wonder just how robust this thing is, right? So if I give you, a different kernel and, a completely different system, right? So I mean, if things are actually pretty different from the system that you considered, right?
Yeah.
I mean, how robust is this thing? Will it really identify correctly all of the critical tasks and so forth? Or maybe, another way to ask this question is, have you encountered some corner cases where you know something should be accelerated, but your system is not picking it up?
Yeah, actually, although our scheme does not require any guest OS modification, but it needs to access the kernel symbol table for virtual machines. So actually, obtaining the kernel symbol table is generally not very difficult in many cloud systems. But if the malicious users can provide the vulnerability kernel symbol table, in such a case, our basic scheme may accelerate some operation. But we believe the cloud providers, the hypervisor or administrator, may need to inspect the kernel symbol table for the case. Or in public cloud, for example, Amazon has already provided the virtual machine images with the kernel symbol table in their image. So I believe it is, in common case, it will not be difficult.
Okay, very nice talk. I have 3 questions. First, it seems that if I understand correctly, you need to first observe that a vCPU is yielded. Then you need to look at the siblings to see if there are very important things going on. Then you can boost those preemptive.
Could you speak slowly?
Oh, okay. So it seems that you need to first observe a vCPU yields to the hypervisor.
Mm-hmm.
Then you will look at their siblings to see if there are important things going on that you can move them to micro-sliced cores to accelerate them.
Yeah.
So my first question is, so what if, or if there a more general approach that without a CPU yielding to the hypervisor, then you can still periodically or other event-driven to look at if preempted vCPUs should be accelerated.
Yeah, the more general way is maybe whenever a virtual CPU is preempted, we may want to inspect the instruction pointer instead of just inspecting the instruction pointer on yielding events.
Okay, yeah, that answers the question. Yeah. The second question follows the other. The question is, so what if the critical operations are implemented in the user space? For example, there are a lot of synchronization primitives, spin logs implemented entirely at the user space. Then for this case, you won't be able to monitor or detect in the kernel symbol table. Yeah.
Actually, we in this study we focus on the critical section used in the kernel of the critical section of the kernel operating system, but we didn't consider the critical section such as in the user level, because this problem we've seen that very frequently occur in the kernel instead of the application. That's why we focus on the kernel execution.
Okay, so the third question is, so you have a very small time slice in a micro slice kernel course. So how would you determine when to migrate the accelerated vCPU back to a normal CPU?
Whenever we give a short time slice in this study, we just give a 0.1 millisecond for a virtual CPU to run on the micro slice pool. After the 0.1 millisecond, it automatically goes back to the normal pool. Okay. Because we do not want to some virtual CPU occupy the micro slice pool.
Okay, thank you. Overall, this is a very nice work. Thank you.
Thank you.
Thank you. How do you assign a budget and period in the fast mode? Is it a heuristic method you use? So when you change the budget and period to the shorter one, how do you assign them?
You mean the budget, the time slice, or?
Yes.
We didn't dynamically change the time slice for each CPU pool. We just fix the time slice.
So you have only two type of time slice when they run in a normal way, and then when you detect a critical one, you move to another one.
Yeah.
Okay, thank you.
Thank you.